Hi, it's my pleasure to introduce Himal Kumar, the co-founder and CTO of Canopus Networks. Today is going to tell us about their experience doing measuring broadband experience using P4-Push telemetry. Himal, please take it away.
Thank you. Thank you so much, Meera. I am Himal, co-founder and CEO of Canopus Networks, and Canopus Networks is based in Sydney, Australia. I'm going to be talking about measuring broadband experience using P4-Push telemetry. So let's get started. So traditionally, and even today, internet plans, ISPs, marketing, all is based on speed measurements and how fast is your internet, lightning fast internet, and megabits per second. But that's not always the case when it comes to applications. Applications care about experience, subscribers care about experience. Not always bandwidth and speed is important, but it is necessary. Given the complexity of application in today's world, they depend on various factors, not always the speed. Talking about, let's say, download, user would care about download speeds and upload speed in that case. But for a streaming video, what's the resolution of the video, or the buffering states of the video is more important than how much bandwidth is available. And content providers have put in tremendous effort to invent very cool algorithms to pack more in lesser bandwidth. So in that case, bandwidth kind of becomes irrelevant. And also, streaming video, the more bandwidth you throw at it, it'll consume more and more. It'll switch resolutions, go over to 4K. So that doesn't really solve the problem. Same with live video. People care about if it's grainy, if it's jumpy, are we losing packets because of which it's skipping? And if you're in a live tournament, if your neighbors are cheering before you, that's what you care about. In gaming, gamers care about latency and jitters and not about speed or bandwidth because usually gaming streams are very thin and they only need kilobits per second. So throwing gigabits per second of plans doesn't work for gamers. And for conferencing, similarly, depends on dropout, if you lose a connection, if there is stutter in the video, and so on. So that's what we do at Canopus. We try to measure experience per application as perceived by the user and not just define the experience based on bandwidth and speed. So I'll talk a little bit about the technology. How do we do it? So we call the technology as flow pulse, and pulse is just a heartbeat of a flow defined by a 5 tuple. So what happens is, as you can see, there is a P4 programmable switch. We use the Barefoot Intel Tofino chip on these switches. So all the traffic as a tab, so this is all out of line in the network. All the traffic would be plugged in on the switch. And what happens on the switch is every flow is isolated, every flow of interest as a 5 tuple flow. And then on that flow, we run basically we extract the telemetry of that flow, which is a time series of many attributes. And those attributes could be time series of byte counts, or they could be of packet counts, or they could be some header attributes as well, such as packet inter arrival times and header information, application level header information, and so on. All this information is collected together and sent out on a data port in the form of a packet called a postcard, as you can see here in the figure. All these postcards are then collected in the compute and aggregated, and what we generate is called the flow pulse of a flow. And these are a few examples. The flow pulse of a Netflix looks like this, which has a spiky pattern because Netflix works as fetching a chunk of a video and then goes idle, and then fetches a chunk again, goes idle, which is the buffering event. In case of a Twitch, the spikes are closely placed together because it's a live video and the chunk fetches happen more frequently in real time. Skype has a continuous pattern of fetching content, and this one shows a Steam download, which is a chunk-based download. It looks completely different. So even just by looking at them as a human, you can distinguish what kind of traffic that might be. So all these profiles, time series profile, are fed to our machine learning pipeline, and those models are able to infer what application it is, who is the provider of the application, and what type of traffic it is. Is it a Netflix download or a video? Or is it a gaming download? Or is there actual gameplay going on? And we are also able to infer the associated user experience, those user experience metrics I talked about associated with these applications such as gaming, streaming video, live video, and conferencing. So that's how the flow pulse technology works. And so we get this power of P4 plus Tofino, and it gives us few very good to have features which were not available before we had P4 programmable data planes available in the world of OpenFlow, which was our first version of the product. So some of the features that are very useful is it's a push-based telemetry, so that which means it doesn't put a lot of pressure on the control plane. We don't have to pull the switch. We don't have to pull a control plane to get all this information. All the telemetry is pushed out on a data plane packet as out of the switch to compute, which helps in scalability tremendously. The switch and the chip is highly programmable, so we have a very quick turnaround for new feature development, rapid delivery. Some features can be just implemented in few days or weeks, and we have the flexibility to control from a company perspective or product perspective whatever need to be done specific to the application or the use case without waiting for standardization and standard protocols. Some of the features that also are very useful is just mirroring large amounts of traffic to compute different containerized applications and cloud native applications which are completely distributed. The right traffic can be filtered and sent to the right place in compute in our system. And then we have access to registers on the data plane, which is great for maintaining states and doing a lot of stateful processing on the switch. So that's how the system essentially works. Now I'll talk a little bit high level architecture of the whole system. So we have like three layers in here. The scaling layer is the P4 programmable switch. And as I talked about, this gives us majorly three functions. The first one is filtering of the traffic, basically, and decapsulation of the traffic. What flows need to be sent where, what traffic needs to be sent out of which ports to different compute devices, and removing or adding all the encapsulation of the packets, which the computer or the application don't really care about. So all that filtering happens on the switch. Second is extracting that telemetry, the time series profile and the stateful profile, which is maintained in registers and so on. The third function would be suppressing a lot of traffic in the switch so that compute hardly sees not more than 20-25% of the actual traffic. A lot of it, which are in terms of long flow, is suppressed and held in the switch, and we just export the profile of the flow. So this helps in scaling quite a lot. That's why we call it the scaling layer. On top of that, we have our packet processing engines, the data collection platform, which collects all this information, where all the machine learning models and all the inferencing happens, and then all that information is held in the system, which goes through an application broker or filter, which passes on that information to different, what we call as Canopus apps or third-party applications, if could be also built on this data, which are directly tied to business use cases or business applications given meant built for internet service providers, which would solve a specific business problem based on the data that's coming out of the platform. And examples of those use cases or applications are UX assurance, which is pretty much talking about how do you measure user experiences of all the application and assure that your customers are getting what you're promising, how your network is behaving, how the changes in the network are impacting the user experience in real time. And other use cases are forecasting which applications are growing, how your traffic is changing, so that you can optimize your network for those, such as the gaming events happening or gaming downloads happening impacts the network significantly. Comes under network optimization forecasting. Operators can also launch premium services, and we've seen gaming being done by many in the industry, where gamers can get a premium service for a better gaming service where they can themselves see what is the performance of the games, what are the latency and lags, and then you can make changes in the routing and send it on a different path, low latency path, based on when you know which traffic is your gaming traffic. So then you can actually take action in the network to offer those services. customer segmentation, marketing, and ultimately the vision is for self-driving networks, which is looking very promising in the 5G world, where you'll be able to collect a lot of data from the network and all the application and collect all the performance metrics and use it to self-optimize and self-drive the network by taking actionable intelligence. That's pretty much all that I wanted to talk about today. And thank you so much, Meena and Michelle.
Thank you. This was really interesting. So I'm gonna maybe ask a couple of questions. I think the first question I want to ask is about kind of your experience with implementing telemetry on programmable data planes. So while you were kind of implementing flow pulse or creating it, were there any data plane or control plane features that you wish was there or would have made your life easier, and or you would suggest, people who make programmable chips or kind of work on P4 to add to the ecosystem?
Yeah, sure. So I'll start with by telling that back in 2018, our system, the first version of the system was based on OpenFlow, and we had some very serious limitations on the control plane, mostly around how many times we can interact. So we're looking at few thousands of flow mods per second here in the system. So that is the amount of frequency of the interaction between the software and the switch. So that was a serious limitation that was solved when we had P4 runtime available and on the switch, and we had the scalability available. Now we do thousands of flow mods per second without any issue at all. Second was we were kind of limited in the OpenFlow world by having fixed protocols or fixed pipelines, which were very tied to the vendor. So in now we have full control over the pipeline. We can change the pipeline in runtime. We can even change pipeline for different customers for different use case. It can be customized. It can be done very quickly. So that power of having all the flexibility and programmability is definitely very useful to us from a business perspective as well.
Right.
The features I would have loved to have, I think we as a community need to work a little bit more on the documentation because the documentation that I feel is still very behind the technology that we have. So many times our engineers have to do a lot of trial and error to see how this feature would be implemented in P4. So that's one thing we have struggled a little bit, but a lot of those problems were solved by using the ONF stratum, which gave us a pretty good platform to implement P4 runtime on the switch. But again, I feel there's still a bit of lack of libraries available for interaction with the P4 runtime, like standardized libraries. So we pretty much have to implement that ourselves. What more in the data plane could be great? So sometimes our customers ask for cloud native deployment where we don't have the luxury to put a switch in. So we're kind of keeping an eye on technologies such as P4-NICs or virtualized P4-NICs. In cases of where the deployment is pretty small, we don't have to achieve scale of terabits, or it's a complete cloud native deployment where you can't really insert any hardware yourself at all. So I think they would be pretty cool to have in the coming weeks or months. Yeah.
Right. Yeah, that would be very cool. Great. Another question that I had was about kind of the machine learning part of your system. Could you give us kind of a sense of how much data or features you actually needed to kind of extract from the network in order to kind of effectively train the models that you're using? Or is it kind of a continuous training and it kind of goes on as the network is running?
Yeah, all right. There are a lot of features that are extracted, and the most simple ones are the time series of byte counts and packet counts, and they already tell you a lot. In addition, you can do packet inter-arrival times, and we also extract features from the application layer. Yeah, sometimes some byte patterns that are available, which protocols are being used, and so on. These are extracted at a granularity of sub-second, usually mostly in the millisecond range. So it's pretty fine grained, and the classification and the inferencing of user experience can take less than 5 seconds sometimes, or can sometimes take up to 30 seconds as well.
Right. Right.
Are they continuously extracted in the live production system? No. Once the inferencing is complete, for the classification, then we don't extract that information continuously, but we might extract that information which is relevant to classifying the user experience because that's a continuous activity. Otherwise, the training happens in labs where we label all the data and keep extracting these kind of information to train the models which are sent to the
I
field.
see. I see.
Does that answer your question?
It does, yeah, no, and I'm glad you said lab because I was thinking if you're extracting things from the application layer, I was wondering how you're doing it in the data plane, while the kind of traffic is going through.
So
So that,
some of the features are extracted in compute as well. Not everything is just extracted in the data plane because there are a few features which are very hard to implement and have very complex logic to implement.
right.
So that's why we do send filtered some sort of selected packets from the data plane up in the compute. And
Right.
then that information is combined. Yeah.
Right. Great. And did you find any privacy concerns regarding kind of this kind of monitoring and telemetry on network traffic?
So one great thing about the way we have approached the whole this problem, because DPIs has been around like forever, right? And deep packet inspection, and that is invasive. But the way our technology works is we are not looking into packets. We are not looking into content of the packets. We are looking into behavior profiles and byte counts and packet counts and so on, which are not sensitive features. And even when we do classify a certain application for a flow, we never in any of our deployments have information to associate any classification to any subscriber per se. So in that way, we kind of go around this privacy concern because we never get that information. We never look for that information,
Right.
and it's a different approach than deep packet inspection. Yeah.
Very cool. So I was also having kind of as the last question, more of a discussion point, maybe I was wondering if you could tell us kind of about one of a more kind of concrete use case. You had kind of some classes of use cases on your last slide. But if you could pick one, maybe a concrete use case that has kind of benefited significantly from your system and kind of tell us more about it.
Yeah, I think one of the most popular use case is measurement and tracking of user experience for
Mhm.
streaming video and gaming both together, because both of these applications are critical. And whenever there's a change in the network infrastructure or the plans are being sent, usually ISPs don't have a deeper idea into what exactly the user experience as perceived by the subscriber is.
Right.
So when the rollout of 5G is happening, people are moving from 4G to 5G. How is it performing? What are the applications actually doing in terms of performance is one pretty big use case. And one of them is also around the performance of fixed wireless networks,
Right.
which is a big one. Another big one is around gaming. So in gaming, there are two different kinds of use cases. One from an operator's perspective, when if they are running a premium gaming service to consumers, they are marketing a premium gaming service. They want to make sure that all their gamers are happy and they are getting the performance that their network is tuned for. So then again comes in the assurance, but also sometimes there are use cases where we deploy the system closer to the gaming servers in CDNs or data centers which host gaming servers. And
Right.
from that point, we can measure the performance of gaming servers, latency, and lags to only for the gaming streams.
Right. Right.
Yeah.
Very cool. This was all very interesting. Thank you so much for the talk and for answering all my questions. I think this is it for me.
All right. Thank you so much, Mina and Michelle, for arranging the talk.